All right, so today we're going to talk about some repeated measure stuff, uh, which really like mixed effects models is what we're talking about. Before we get to the actual thing today, first there's a new package this week. LME4 is the mixed effects models package that we'll be using. So make sure you get that installed. And I wanted to give kind of take a step back and give kind of a broad overview about this unit in particular and where it can go. Bill's summer class is basically an entire class, a course that's on mixed effects models and multi-level modeling and things like that. And really what that whole thing comes down to is the same thing as this. And like if you can get your head around this, then once you get into that, the application will be simple and straightforward, and it's more so at that point connecting the conceptual things. When it comes to mixed effect modeling, really what it comes down to is being able to understand the conceptual link between your research design and like, well, what random effects am I specifying and what fixed effects am I specifying? So, in the examples that we'll use today and that were used in class this last week, Patrick was talking about, 2 reviews from 1 reviewer. And so like the unit in that is like the individual, it's that individual within subject, variable. But for instance, this can be scaled up to any number of things. If you're doing survey research and you send out, some survey to high schools around the state and you're looking at, some specific behavior, you'll probably want some sort of grouping for that where you're allowing things to vary within schools, because just like you would expect, socioeconomic status to differ between this school and this school, you're going to want other things that may systematically vary, or not systematically but randomly vary. And so instead of grouping at the individual level, it may be like grouping things within school, or even like in one school within like different classrooms, and looking at kind of like the teacher as this factor that differentially influences all these different things, blah blah blah. And so basically once you get into Bill's class, it's all looking at this stuff, linear mixed effects, and then it's just a matter of figuring out, based on this design, like what am I specifying as my random effects and things like that. Because also depending on the design, as we're doing it today, both the intercept and the slope are random effects, but depending on the design, there may be designs where you allow the slope to vary randomly, but the intercept has to be held constant, or the other way, that like you have a random intercept but a fixed slope or whatever. And so basically just the point that I'm trying to make is that like this last unit is definitely something that will carry forward, and if you can understand it and be able to apply it at this real basic level, then it'll just be a lot easier for you once you move on to like a mixed effects modeling class and get into more complex designs.
Another question.
Mm-hmm.
So for my research, would that apply to a situation in which I wanted to look at differences between like time of day that the studies are ran, or even first half, second half of the EG session?
Yeah, you could do that. Like as far as time of day, like that would be like only if you were using that same participant like across different times of the day. Because if it's like the morning participant versus the afternoon participant, now it's a between subjects. It's not a within subjects thing, and we'll talk about that. But like if you are looking at the first 2 hours of the session versus the second 2 hours of the session, you're getting that same thing, then you are looking within subjects. And so you might look at that as a random effect. And we'll talk about that here in a little bit and see if you see that parallel there. All right, so I just went ahead and gave both the wide and long data frames. And And so when we look at this, we can see that this is the exact same information, only up here in the wide data frame, we have so what this study is looking at is the effect of alcohol on fear. And basically, there's a difference between fear and anxiety, where fear is, kind of a fear of something that you're expecting, whereas anxiety is more of a fear of something that you aren't expecting. So in this, they had participants drink alcohol or not, and then there are two conditions, a predictable condition and an unpredictable condition. And the predictable condition, as they're going through these series of stimuli, every time there's a square, they get shocked. And so when you see a square, you know a shock is coming. And so it's a predictable thing, but there's still fear of that shock. Whereas in the other condition, it's a random, as they're going through the stimuli, it's a random shock. So you never know when that shock's going to come, which is what they're, operationally defining as anxiety. So they're looking at the startle response to the shock as a function of whether they knew the shock was coming because they were in the predictable thing. They see a square, the shock is coming, so how did they startle? Versus how do they startle in the unpredictable thing when they don't know when the shock is coming. And then the between subjects factor is whether or not they drink alcohol. So in this wide format, they have two scores. These are the startle responses for the predictable condition and for the unpredictable condition. In this long data frame, it's the same thing, only now each participant has two rows. And you can see when we look in the long data frame, each participant has two rows. One that has a startle response for the predictable condition and one that has the startle response for the unpredictable condition. So we'll be going back and forth between the long and wide data frames, but it's the same data, just structured differently. In this, one thing to note is that the independent variables are already centered. So coded as negative half and positive half. Keep that in mind when we get to the actual outputs and the analyses. And when we get there, we'll also discuss, because what is the default behavior for, say, this condition column here that is, a character column. If we didn't code this as negative half and positive half, and we just put in, this condition instead, how would R read that? What would R do with this column of characters if we just put that into an equation? Instead of using predict with this negative half and positive half, if we put in condition with pred or unpred, what will R do with that information? How will it interpret it and use it?
Well, just assign a 0 for the first.
Exactly. 0 and 1. By default, R will handle factors as 0 and 1. And so that has implications as far as the interpretations. But we'll talk about that when we get there. And this is just looking at selecting from the wide data frame, selecting the predictable and unpredictable columns and seeing if any is in A, or seeing if any are in A. We can see false. So like every participant was in both conditions for the predictable versus unpredictable shocks. And then just some other general stuff that I put in here kind of because we haven't really done a lot of analysis in the last several weeks. One thing that's somewhat new is this described by, and where I have described the startle by, and if you use list, alcohol, and condition over here, basically that's analogous to using group by. So for this, if say we just wanted the means grouped by those things, it would be the same as saying summarize group by startle, comma, alcohol, comma, condition, or excuse me, DF long, comma, alcohol, comma, condition, and then mean startle or whatever. And that group by function would do it by like a 2x2 type thing. But if you're using describe by, you can put the things that you want to split across as a list. And so then the output here we have our alcohol predictable, no alcohol predictable, alcohol unpredictable, no alcohol unpredictable. So if you're wanting to use describe by to break down by two separate things and cross those factors, then you can just throw it in a list like this, and that's how just another way that you can do that. Correlations. In here, I have a note that, like in this particular case, I went ahead and I included this use pairwise complete observations, which you don't need it. Like if you delete that, you'll get the exact same output for this particular thing, this particular correlation, because there are no NA values. But if you do have NA values in there, and you don't have this use pairwise complete argument in there, then your correlations will all come out NA. And basically this just tells R if there are any NA values, like just remove that pair of values, only use pairwise complete observations so that it's not throwing out NAs. And then, the chart correlation thing, if you want to see the univariate, bivariate, and distributions and the correlations there, that's a great function. So first we're going to take we're going to use the long data frame, and we have to make the subject ID a factor. The reason that we have to make subject ID a factor is because as we're using Elmer, whatever is the variable that is the unit at which we are considering data, it has to be a factor. So when we look down here at M1, this first Elmer model, just as a reminder, it's set up a lot like the LM that we've been using all semester, except for now we also have this stuff in parentheses, which is our random effects. That's where we specify what our random effects are. And so to do this mean only model or the intercept only model, just like we would with LM, like the way you would do that is regress startle on 1, which is not actually on 1, but rather what does 1 represent in like R. Do you remember what 1 means? It's the intercept. Yeah. So, we talked about that a little bit last semester, that, if you have other stuff on the right-hand side of that tilde, then the 1 is implicit and you can leave it off. But if you are doing an intercept-only model, then you have to explicitly put it in there. And as we'll see later on, the same thing applies over here within the random effects, that over here we're also specifying that the intercept only can randomly vary by subject ID. But if we had some other variable that we were allowing to be random there, then you can put 1 plus whatever that thing is, or you can just leave the 1 off. Before I go on, I'm going to scroll down. I'm going to run this code to make this plot real fast, so we can talk. Because, one thing Patrick talked about was that as far as why it's called random effect, and he kind of talked about that it's kind of technical, and I don't know how much he's going to get into it, but I wanted to give you kind of my layman's understanding of, or the way I conceptually think about what it means to be a fixed versus random effect. So this is similar to the graph that Patrick showed in class this week, and basically it's just for each participant, it has like their predictable and unpredictable responses. And that horizontal line is the mean. And so you can look and you can see that the slopes are all different for all these participants. And then, the means, here's the mean of this participant, here's the mean. So the means, also that intercept is also different for each participant. And the way that I think about this is what you're telling R here is that you are, the way that when you consider a linear model and you have your additive versus your interactive models, and like what the difference between those are, that if you have an additive model, you force the equation to keep everything the same. But when you add that interaction, now you allow the other thing to have a different value, and that's what those interactions are. So this, you can think of this, the random effects, as a way of telling R, like, I am allowing my intercepts to vary randomly, and I'm not forcing like an assumption that all of these things have the same intercept. Specifically, I'm allowing the intercept to vary randomly amongst the subject ID. So like that is the like specifying that random effect and saying like, I'm not gonna force all of these different things to hold one solid intercept and say that's it. So when we're talking about random effects, you know, you can think of it in terms of like, what are we allowing to have some random variation in there? And so in this case, with the mean only model, with the intercept only model, for the fixed effect, we're looking just for the effect of the intercept, the mean only, but also allowing the intercept to vary randomly between subject IDs. For today, we're just going to focus on the fixed effects portion of the output. We're not going to really talk about the random effects stuff. And
did you add that one there?
Where?
So on the equation, you have the startle tilde 1, and then the brackets. Ours doesn't have that first one.
The 1 plus.
Yeah, 1 plus.
I don't think it matters because it's.
So is that what you were saying?
What is it?
I'm saying our equation doesn't have that first one. 1 plus.
Oh, it should.
Will it change anything?
Well, will it run without it? Oh, well, never have it. Maybe you don't. Either way. So again, all we're looking at today is the fixed effects, and I put these in this capital A ANOVA type 3, and just as a reminder, the only reason to run that is if you're trying to get the p-value for your things, because Elmer, it won't put out the p-value. Alternatively, if Elmer puts out a t-value, you can convert a t-value to a p-value. Or if you run this capital A ANOVA function, it'll output and tell you the p is less than 0.001. But looking at the fixed effects output here, we see that our estimate is 37.21. So what is that value? Like, what does that represent? 37.2. It is. It's the grand mean. And if we look at the mean of all the startles responses, we can see that the grand mean, sure enough, is 37.21. If we go to the wide data frame, and here, just run this line, all I'm doing is I'm creating the mean of the predictable and unpredictable responses. So when we look in our wide data frame now, I just created this variable called startle that is just the mean of these two values is 82.6, and the mean of these two values is 83.1, etc. So now I've just created a column that is the means of these things. And then if we take the mean of that, again, 37.21. So just trying to re-emphasize that. And then now that I have this startle variable that was a manually computed means, if I create a model that now I'm just using LM instead of using Elmer, because I'm using the wide data frame, and if I just do an intercept only model for that average and look at the summary, it's the exact same, 37.21. The standard error is the same, the t-value, everything is the same between them. So this is what Patrick was talking about this week, as far as basically when you're specifying a mixed effects model, really you're doing two things. Like, first you do a series of mini regressions that's broken down by whatever unit you specify. So the unit that we specified was subject ID. So it will break the data down by subject ID and do these mini regressions on it. And when you look at regressions on the mean of some responses, that's your intercepts. And then the regressions on the difference between those two variables are your slopes. And then, so after doing those mini regressions, then it moves on to that second stage or phase, whatever he calls it, and looks for those fixed effects of other things. And so now, does alcohol significantly affect the startle response? So now the only difference is we're back to Elmer, and we have, we're going to be using, which means we're using this long format, and we have, we're looking at startle. So we're looking at this column right here as our outcome variable, and we're regressing that on alcohol C, this centered alcohol thing, negative half or positive half. But then our random effects, we're still allowing the intercept to vary randomly within subject ID. And when we look at this output, again, just looking at the fixed effects only. So if we have this coded as negative half and positive half, for no alcohol and alcohol respectively, what does this intercept here tell us?
The average for both conditions.
Right, so it's again, the grand mean, the average startle response collapsed across conditions, and then the alcohol C, or alcoholic, I'll call it, is what? What does that value tell us?
It's the difference between the alcohol and the non-alcohol.
Exactly. So if 34.5 is our grand mean, and the difference between the groups is 15.13 points, then how do we figure out how much a soap per person startles on average?
Add half of the alcohol effect.
Exactly. You just take this and split it and add half to that and subtract half from the other, and then you just have to figure out based on how it's coded, which mean belongs with which group or whatever. But yeah, so like, as far as interpreting these things, like nothing has changed. It's still just, thinking about what does 0 represent in this data and interpreting that output the same. So earlier I talked about how, in this particular case, the data set that you were given was already coded as positive half and negative half, but let's say that it wasn't, and instead you put the alcohol variable where it is a character, and now it's 0s and 1s. What would this intercept represent?
The average of the no alcohol.
Yeah, whichever one was coded as 0. Right. So, and then this would be what?
It'd still be the difference.
Right, but now instead of, and so if you were trying to figure out how much the other group was, you just add the whole thing. All right, we all tracking on that. So if we, I'm just gonna cruise past that portion, so it doesn't really matter. All right, so here, like I emphasize, like, don't come back to this drill script and look at M5 as an example of what to do, but instead what I'm doing here is I'm taking that same model from model 4, which is the exact same as model 3. Again, like, this is just doing it by the wide format, we would use the just LM and regressing startle on alcohol C. So again, that's just putting the means, regressing the means of their two responses on whether or not they're in the alcohol condition. But if we take the same model, but instead use the long data frame. So now we're taking startle, which is right here, and regressing it on alcohol C over here. Compare that model 5 with model 4. And so again, here we have the long data frame, and here is the wide. So this one is correct. This is that model 4 that we just ran. And you'll notice that the parameter estimates are exactly the same, but the standard errors, you're getting smaller standard errors up here when you run it in the long data frame. Why is that?
Got 2 rows for each person, right?
Right, yeah, because you have 2 rows for each person, so you doubled your sample size, but you didn't actually double your sample size. You're just R is assuming independence between everything because that's what you put in there. So you effectively double your sample size, which reduces your standard error, and that's a problem. So that's why you got to be careful and think about which way you have your data laid out. Because again, either way, regardless of whether you use LM with the wide data frame and just use the mean variable as your outcome, or the difference as the outcome, versus using the long format where you're just using the startle variable, but you're allowing that random effect of subject ID. You just have to make sure that you have things laid out the correct way. And on the homework this week, which is already posted and it's just set to become available at 10, that's basically what you're going to be doing, is working through a few different models, basically doing it each way. Like do this using Elmer and then do it using the wide format. But again, you're given both the wide and the long data frame, because I don't want y'all getting lost in the weeds of structuring your data. Just focus on making those connections between the structure of the data and the analysis that you're trying to do. So yeah, you have the wrong denominator degrees of freedom when you apply that LM to the long data frame, because you have twice as many rows, and that's no good. So we already ran that plot. All right. So take a little detour here, because now we're going to look at if predictability significantly affects startle. So whether or not knowing that a shock is coming or not knowing a shock is coming, and what does that do with the startle? So I have this line here, Elmer control, and I'm storing it as control X. And I have a note that after today, I'll just, this will be control, but I wanted to use control X today just so that when we get to the models and you see control equals control X, you make the connection between, oh, this is where we're plugging that in, instead of it just saying control equals control, which some people, might get a little confused on. But for this right here, basically you just need to copy and paste this line into future scripts when you're using Elmer. I'm not going to really get into, I'm not sure how Patrick's going to get into this. He talked a little bit about this optimizer thing, which has to do with algorithms and what goes on under the hood, blah, blah, blah. And so with this calc grid, you're saying false, because that's telling you that you don't want to compute the gradient and Hessian of nonlinear optimization solution. That one, I can't really tell you about, because it's above my head. All I know is that there are various different algorithms that can be used for some stuff that goes on under the hood. And in this particular case, or well, unless you're told otherwise, you're going to want that one to be false. This one is check the number of observations versus the number of random effects. And that has to do with if I come down here and just take out this control thing so that we don't use that, it's going to throw out a warning, and it's going to, or an error rather, it's going to say that the number of observations is less than or equal to the number of random effects, because there's 136 of each, and like, oh, you know, Elmer's head just kind of implodes. And so this is telling it to ignore that error, because otherwise it won't run. But once you ignore that error, the thing runs just fine. So all you really need to know is just remember that you need to come back and copy and paste this control line of code into Elmer scripts. And you don't have to use these controls on the more simple models. You know, with those, the ones we've already run a couple Elmer models, and none of them threw this error, because it's not a problem with very simple models. But as you get into more complex models, which is where we spend most of our time, it is a problem. And when you take Bill's mixed effect models class, like he will get into some more of the under the hood, like why this is the case and what it's actually doing and why it's a problem if, you know, your number of observations is this and but your number of random effects is this other thing, blah, blah, blah. But for now, all you need to know is that you need to include this control variable, and that just consists of copying and pasting this line of code into your other scripts. All right, so let's break down Model 6 here. And like, what is this portion? Fixed effects, exactly. And so for our fixed effects, we're just wanting to regress startle on predict, whether it was predictable or unpredictable. And then over here in our random effects portion, what are we telling R there?
You're allowing your coefficient predict variable to vary randomly across subject ID. Yeah, basically, you know, and implicitly here, because we don't have it, or this might be where y'all actually do have a 1+ in your script. At some point, there was a place where there was a 1+, but even though I didn't have the 1+ there, it was implicitly there, which means the intercept and the slope of predict are allowed to vary randomly within subject ID. And then for you know, control, ignore this warning, blah, blah, blah. And then we look at our summary. And so looking at our fixed effects here, this estimate, the intercept estimate tells us what? Grand mean, as always, and the predict slope estimate tells us change across. Is that condition?
Yeah, but like, just one thing to keep in mind is that whereas before, everything we've done up to this point, this would basically be the difference between participants who were in the predictable condition versus participants who were in the unpredictable condition. But now, because that's a within subject variable, it's the average difference for participants, like average difference in startle response between the two conditions. So the interpretation conceptually is the same. You just have to think about the unit of measure that now we're not looking between groups, but rather just between responses within any given individual. On average, the difference is -1.7. And so if we look at this and we do described by...
Can you say that interpretation one more time? Like, I understand it, but I just can't write it in a sentence right now.
Yeah, so the average difference for participants, the average difference in their startle response to the predictable versus unpredictable condition. So same interpretation as before, except for saying the difference between the group that did this and the group that did that. It's the average difference when a participant did this and that same participant did that. And so when we look at described by, and if we describe the startle by prediction, we see that on average, the average startle response for the group that's coded -half, or for the, not the group, but for the condition that's coded -half is 38.09. The average for this one is 36.34. And when we check that out, we see that, 1.747 is the difference between the average startle response for one condition and the average startle response for the other condition, which is our difference there. And so this is talking about how, essentially this runs regressions with the two different DVs. Again, that random effects is kind of like a series of mini regressions. And a regression on the means would be the intercept, and then the regression on the differences is going to be your slopes. As far as like how much does a person on average respond to an unpredictable versus predictable shock, same thing that we did earlier. It's you split whatever the average difference is and go half of that above and below the grand mean. So here there's just a reminder that whenever you're doing things within a model, if it's on the left-hand side of the tilde, you can do arithmetic. But if you were over here on this side, on the right-hand side of the tilde, in order to do arithmetic, you have to wrap it in that capital I parentheses function, because otherwise R will read, a plus sign or an asterisk as like, the effects, instead of like looking at it as this plus this. And so all this is doing is, instead of manually computing the average of predictable and unpredictable and storing that as a variable, and then manually creating a different score and storing that as a variable, just doing it in line. So here, all we're doing is we are creating the average of these two and doing an intercept-only model. And then here, we're creating a different score of these two and doing an intercept-only model. And so, in short, like, an alternative to doing this is doing mutate, DFY, mean equals predictable plus unpredictable divided by 2, diff equals unpredictable minus predictable. And now if we had that mean and diff variables, and instead said LM mean regressed on 1, LM diff regressed on 1, exact same thing that we're doing here, but just not creating a new variable and putting it in the data frame. But again, when we run these 4 lines right here, we get our summaries. For the different scores, our estimate ends up being -1.7. For that mean, our estimate ends up being 37.21. And again, when we look back up at our Elmer model, that is what our intercept and slopes are. So just trying to re-emphasize that all it's doing is that series of mini regressions, and the regressions on the mean is what your intercepts are, and the regressions on the difference is what your slopes are. So does shock affect startle differently depending on the level of alcohol? So now we're doing, we're having an interaction between the within and between subjects variables. So as far as the Elmer code, again, nothing mind-shattering here. We're using Elmer instead of LM. We include our control variable. And then we have fixed effects of the prediction condition, alcohol or not, and their interaction. And then for our random effects, we're allowing predict to vary randomly within subject ID. So why do we have predict over here in the random effects, but not alcohol?
Because they didn't experience both alcohol.
Exactly. Because every participant has 2 predict scores, but every participant only has 1 alcohol score. So alcohol does not vary within participants. It only varies between participants. Same thing if you had, if we were including, gender in here. Gender is not going to be a random effect. It is going to have some fixed effect, and it's not going to vary within participants. So you can only have random effects of things that do have that each participant has both, things. So now we look at this output and looking at our fixed effects down here. We have the same interpretations that we've had before. The intercept is our grand mean, collapsed across both conditions. So collapsing across whether the alcohol conditions and across both prediction conditions. We got our grand mean here. What is this estimate here? The predict, we have a slope of negative 5.4, 5.5. What does that tell us?
Change across the prediction conditions for a given individual holding alcohol condition constant.
Exactly. That is the difference between, basically we expect a 5.5 point difference between the startle response and no startle, or between the startle from the unpredictable condition and the predictable condition collapsed across alcohol. Then here for the alcohol thing, it's collapsed across prediction. What is the effect of alcohol? And then the interaction tells us the same thing it's told us all along, that for each 1 unit increase in prediction, the effect of alcohol is expected to change by 21.2, or for a 1 point increase in alcohol, the effect of prediction is expected to change by 21.2. And then here again, same thing, just looking at, if you look at an intercept only model looking at the mean, you get 15.13, and then when you look at the differences, you get 21.2, and that is the same thing that you get up here in this other in your Elmer model. I also went ahead and threw this in there just as kind of a refresher, as far as, yesterday somebody was asking me about, the relative merits of centering your variables and doing that negative half, positive half coding versus treating it as factors and using zeros and ones. And basically what I told them was that by and large, it's user preference. Sometimes there may be something in particular that you're more interested in, and it will make more sense to do it one way or the other. Oftentimes, it doesn't matter. It's 6 of one and a half dozen of the other. Patrick pretty strongly prefers centering everything. I generally prefer leaving everything as 0 and 1 unless I have a specific reason to center things. And because, for instance, if I am interested in like the actual group means in particular, it makes more sense to leave it as factors, where I know that, this is the average for, the no alcohol group predictable response or whatever. And then for the predictable response, I just add that to that to see what the alcohol effect is. Then I just add that to that. And then this one over here would be for, that fourth group. And so like figuring out group means can be easier than thinking like, okay, well, I need to split the difference of this slope and go half above and half below the intercept, blah, blah, blah. So like if you're interested in being able to easily know the group means, it might be easier to use zeros and ones. Oftentimes for plotting, it's easier to use centered variables just because of the way ggplot works, and being able to automatically just put 0 in the middle and split on either side of that, and not have to specify that your x-axis needs to be -1, 0, and 1, or whatever the case may be. So it's different strokes for different folks, but ultimately don't forget that, I mean, if you're interested in group means, you also don't have to figure them out based on your regression output, but rather just summarize it. So here I'm just taking the long data frame, piping it into group by, and I'm grouping it by alcohol and predict, and then saying give me the mean startle response. And so here is the mean for the alcohol group, that the prediction is the -half group, alcohol for +half, no alcohol, blah, blah, blah. So I just wanted to throw that in there because, again, like I know we haven't really been doing a lot of analysis stuff lately. So then looking at this one, this is just another reminder that first we'll look at the correct model and then look at our second model. And so the correct model up here, and this is when we do the long data frame, but using LM instead of Elmer. Again, same estimates, smaller standard errors. And it's the same problem that we had before. It's because our denominator degrees of freedom are wrong, because we artificially doubled our sample size without controlling any of that. And so that's all I have for today. Do y'all have any questions on anything really?
For the correct model, where do you find your degrees of freedom?
Up here in the Elmer?
Yeah.
Well, that would be.
Just compare.
132 degrees of freedom. Oh wait, or is that it? Yeah. Oh, the right. Nova M8. That actually. What would the degrees of freedom there be?
So it has the number of observations.